Hello, I'm Javier. Let's wait for some minutes if someone is coming some seconds later. So let's wait. So hello everyone. I think that we have already waited. If someone wanted to come a little bit late. So I'm Javier Donoso. I work at Gelato. I'm leading the DevRel department. And today we're going to see how can we leverage web randomness VRF on Shape Network. Let's rocket together the Shapecraft. So before we start, I'm going to do a very short introduction about what we are at Gelato, what we do, so that we get to know us a little bit better. So we say the Web3 services. We call us the Web3 cloud platform. And we do mainly two things. We provide block space and we allow users to use different services on this block space. That's why we are a rollup as a service and we provide different rollups, but also we provide some services for these rollups like functions, which are automations, relay, which is a way to sponsor gasless transactions for your users, and randomness. And VRF is the subject of this workshop today. VRF is already available in Shape, and let's have a look how randomness works with Gelato, what is the importance of randomness on chain, and how can we leverage Gelato VRF on Shape. We're going to be hands-on with some contracts and some tasks. So let's have a look first how it all works together. So we think about VRF. We know that one of the main importance for VRF is that it cannot be predicted. And we know how blockchain works, and we know that we have mempools and we have blocks that are created by the miners. So we need a way to define, to clarify, or to get some verifiable randomness on chain. There are multiple applications of randomness on chain. We have gaming and gambling, we have decentralized finance, we have NFT generation. Imagine that you have 500 NFTs and you want, and some of them have distinct traits like hair, skin color, different type of images, and also for gaming and gambling. Imagine that you have a fight and you require different outcome for every fight between two characters. So you can also leverage Web3 function and VRF and randomness for this. So let's start having a look at how it works in one schema, how it works. So we have a user that is requesting a randomness to a contract. This contract is on chain. So this contract, when the consumer requests the randomness, the user can request a card game, can request whatever method that requires randomness. So this consumer contract will emit an event, randomness requested event, and then we have a listener that is listened to these events on Shape network. And when this event is listened by our VRF Web3 function, we will then get verifiable randomness number from the rand, and we push on chain. We will verify in our backend, and then we will push the random number on chain by calling the fulfill randomness method in the contract. So from the perspective of the user, we only need to inherit a specific interface that will emit this event when the user requests randomness, and will have to wait for a method called fulfill randomness to execute when the random number is available. So what is drand? So drand, where we are getting our randomness, is the distributed randomness beacon. And this beacon is part of the League of Entropy. There are different parties that actually is a voluntary consortium providing verifiable decentralized randomness as a public good for anyone who needs secure, bias-resistant, and verifiable randomness. So we can also hear that we, Gelato, we are getting the random numbers from the drand. And the way how it will work, here we have some client libraries. And if we go to the JavaScript one, this is exactly what we do under the hood. We use this client, this drand client, that you can also work in one of your projects. You can use it and test it. And then we will do all of this in our VRF Web3 function that uses this client library to get the VRF number and to push on chain. So from the perspective of the user, as said before, we only need to inherit some methods in the contract. So let's have a look now how it looks at the contract level. So we have here, this is our repo, how-tos on Gelato, and the description, the GitHub repo URL will be in the description below. So let's have a look at this simple VRF contract. We inherit a Gelato consumer base, which we will dig a little bit later. We have an operator address. This is important because if you remember when we looked at this schema, so anyone could call the fulfill randomness. So we must ensure that only the dedicated message sender from this Web3 function, which is a proxy contract associated to the creator of the task, can execute the randomness. So if we go back here, the operator address will be this dedicated message sender that we will define when we deploy the contract, and then this operator address will ensure that only our Web3 function managing the VRF is able to update to call this method. So here we have defined the latest randomness and the last request ID. This is the request that we will be sending, and here we have different mappings and nodes to for the internal logic. So the user is calling the request randomness. This request randomness requires some data that we can pass into the method, so that we can also afterwards get this data when we fulfill the VRF request. So when we do this, we call this request randomness, which is part of the consumer-based contract that we said before. And here what we are doing is we are doing some internal bookkeeping. We are creating the hash of the request, and we are emitting this request randomness event that will be listened by our task, by our Web3 function VRF task. So when the Web3 function VRF task gets a random number from drand and push the result of the random number on chain, it will be called the fulfill randomness. And here what we can see is that only the operator, the address that we define as the dedicated message sender of the task, can execute this function, this method. So here we will do whatever we want to do with this. Here we do all of the different checks, and then we call the customer fulfill randomness method, which is this one here, which is internal. So here, once we receive the request, we have the random number, and we can do whatever we want with the random number. So this is more or less the logic how we approach getting a random number with Gelato VRF. So let's deploy this contract, and let's have a look together how we can create a task that publish the random numbers on chain. So first of all, I have here already prepared. We have here the deploy contract. Okay, join deploy. I'm deploying the contract. It should not take that long. Perfect. We have already our contract. So let's go to our scanner. And here in the ship scan, we can see the contract that we just created. Perfect. This is our contract. So and now we will have to create our task that is listening to the events on this contract. And once the request randomness event is emitted, will trigger the run of the Web3 functions VRF task. This task will get the latest random number from the run and will publish on chain. So this is our app. The Gelato app is app.gelato.network VRF. Here the two important parts are how we can create a VRF task. Here we can create one, and the second one is the one balance. For how the VRF work is that you have to deposit USDC on Polygon, and then it will pay for all of your tasks on all of the chains where we are deployed. It means that you could also create tasks on other chains like Ethereum or Polygon, and you could pay these tasks, these executions with the same balance. Here we have already top up our balance, so we don't need to deposit, but I need to create a task. So I'm going to create a task, and here we have three different options. One is the Gelato VRF, that is what we're going to do right now, and then second we will have another type of task when we are interacting with a Chainlink compatible contract. So it happens that some protocols, they already have created their contracts and audited, and these contracts used Chainlink interface as provider for the VRF. So what we have created is a way to reuse this code, providing an adapter between Gelato VRF and Chainlink compatible interface. We're going to see this afterwards. And also sometimes either it was some problems in the RPC or in the contract or whatever, it can happen that some events were missed in the execution. So you can create a fallback task here that will always check every 30 seconds or every minute whether some events have not been tackled from the Web3 function, VRF task. So you can create the fallback task to ensure that all of the requests for randomness are taken into account. So in order to create the VRF task, we will have to go first and get the address of the contract. We have here the contract. So we're gonna call it simple shape VRF. This is the consumer contract that we just deployed, and I'm going to create the task. I'm going to confirm. So I already confirmed the transaction. We are creating the task. It shouldn't take that long. So in the meantime, we're going to prepare the script to request the randomness. Okay, the task has been created successfully. We can see here the task, and here we will see in the logs when we have the first request for randomness that emit the request randomness event. So let's go here to our code. This is the address. Here we have prepared one script. The only thing that we have to change is the contract. So now let's go here and we're gonna look for the, okay, so let's go here and we're gonna, the name is request randomness. So let's execute this script. We are requesting randomness. This is the transaction hash. So let's go. Let's go to our scan. Here we see that we have the request randomness transaction already visible. And if we have a look into the events, we should see the events right now. In the transaction, we see the events, and here we see this requested randomness event. So looking now at our Web3 function, we see that it was listening to the event and then execute one transaction. And this transaction has already executed the transaction on our contract. So if we go to our contract, we should see in the internal transaction, in this transaction, we should see already that the request has been fulfilled. So it's taking a little bit of time. So let's refresh again. So let's wait until this. Okay, this is a contract. This is our simple VRF, and if we go the / request ID, let's see. So it looks that now the scan is not working as expected, but we can also see here the execution of the transaction. This is this one. Well, it's taking some time, but we can see that the transaction has been executed. We can see it here, and we can also see that it's taking a little bit of time to refresh to the indexer. Okay, here we see randomness fulfilled. This transaction was sent from our Web3 function VRF task, and it did execute it. So perfect. That is the simple example of Gelato VRF. So let's have a look in the second example, and is what I briefly introduced before, is what if a protocol has already the contracts audited in other network where they are using Chainlink for the VRF. So what we will do here is we will create an adapter for you when you create the task. So it means that for you, you don't have to do anything more than deploy the contract as you had deployed on other networks. The only difference is that when you deploy your contract on Shape, you must ensure that you can change the coordinator address for Chainlink, because the coordinator address will be the address of the Chainlink adapter. And we will create this adapter when we create the task. It means that when you can reuse 100% the code that you had already created for working with Chainlink VRF, but you must ensure that you can update the coordinator. So how does it work? It's exactly the same. The user has a consumer contract. And this consumer contract, because was created working with Chainlink, call this method request random words, and it will execute when it goes back the raw fulfilled random words. So what the adapter does is translate these methods into the methods that we have already seen in the first example. It means that for our Web3 function that is calling the DRAM beacon to get the randomness, is exactly the same as before. The only thing that it changed is that between our Gelato Web3 functions VRF that is getting the listening to the events, getting the random number and publishing it on chain, we have a kind of translator adapter that forwards these methods with the appropriate naming into the consumer contract. As it happened before, this adapter can only be executed by the dedicated message sender. And at the same time, this consumer contract can only be executed only by the adapter, the coordinator, because if not, anyone could send transactions. So let's have a look how it looks like in the code, and we will do exactly the same as we did before. So let's go to our code. That was our first example. This is the second one. Here we have we call it the simple Chainlink VRF contract. Here we inherit the consumer base and also the interface from Chainlink. So here we have the coordinator that we will need to change afterwards because we don't know the adapter contract still. It will be created when we create the task. So these are the different parameters that we use, that the Chainlink adapter, the Chainlink uses. Remember here we have a very interesting difference between Chainlink and Gelato, is that Gelato has a cap on the gas limit that the fulfill transaction can execute. In the Gelato VRF, there is no limit. The limit is the block space, basically. So these are different parameters that you can create, you can update for your call. So we have the request like we did before. So here we instantiate the consumer base too with this mock address that we will change afterwards. We have the request randomness here. One difference with the Gelato VRF is that you can demand more than one random number with the same method. You can call 1, 2, 3, the number you want. And here, when we request the randomness, we call the coordinator request random words because that is how the Chainlink interface expects the randomness to be called. And then the adapter that we will deploy when you create the task will do this transformation, and then we call the request randomness and will emit the randomness event that our Web3 function VRF task is listening. So afterwards, we have here the fulfill random words that we can see that is an internal function. So if we have a look into the consumer base, here we see that this method is the method that the chain-link contract is expecting. So, and here we say that only the coordinator can call this method. So we only accept randomness sent by the coordinator to the consumer contract. And then we call the fulfilled random words that we saw that is internal here. So it's worth noticing that here we can set the coordinator once we have created the task. If not, this is not going to work. So let's do exactly the same as before. We're going to deploy the chain-link CL VRF contract. We are deploying the contract. So perfect. Now we take this contract. Let's have a look. Let's have a look in the Shape Explorer. So perfect. 22 seconds ago, we deployed this contract. So now we go to our functions. Here we have our last function running. So we're going to create one, we're going to go to the VRF and we're going to create one chain-link compatible task. So this is shape, and here we're going to paste the address of the contract that we just deployed. So we're going to create the task. We're going to confirm. So now we are waiting. Here we need to wait before. That was not right because I didn't pick up the chain-link compatible task. So we will need to create again the task. Sorry for this mistake. So create task. We go again here, chain-link compatible. And what now the app is telling us is exactly what we discussed before. We should only proceed if the consumer address, the contract that will consume the randomness, can update the coordinator. We have seen before in our contract that we said that we create a method to be able to update the coordinator. So let's proceed. We're going to call chain-link number 2, and this is the compatible. And this is right. Here we will paste our address from our contract and we will create the task. And now we will see 2 steps. First, we deploy the adapter. And once the adapter is created, and this is the address of the adapter, we will have to create the task. The MetaMask is asking me to confirm the 2 transactions. So now we're going to wait until the task is created. What we can see is that here we will be able to see the contract that we just deployed. This is our adapter. So let's have a look. Perfect. The transaction has been created. This is our task. And you can see here that the target contract is not the target contract that we have defined, because the target contract is the contract that inherits the chain-link interface. what our Web3 function task, VRF task is listening is to this adapter that we have created. So now let's copy this adapter. And first of all, let's update the adapter to the new contract. So this is our contract address, our consumer contract. And then now we're going to simply set the coordinator. So now let's set the coordinator. Okay, it's waiting. Perfect, we have the transaction hash. Let's go to the scan. Well, maybe we have already the, let's here the transaction. Perfect, and we are calling the simple VRF contract. Here we see we have setting the coordinator, and we will see in our payload that this is the coordinator that we created in the Web3 function that we can see here in our task. So now let's go back to the contract. And now if we go back to our code, let's copy again our contract deployed. And we go to Chainlink. This is our consumer contract address, and we will simply call the request randomness. So let's call our request randomness here, request Chainlink. Perfect, so the contract address is the one. So let's execute the script again. We have requested, in this case, two random numbers. So if now we go to our scan, we can see that we have the request randomness. Let's have a look at the transaction. We see in the transaction that we have requested two randomness. So let's go back to the contract. And now if we go to our function, here we should see exactly that the function has been triggered twice just right now, because we asked for two numbers, for two random words. So here we must see the execution that also are updated. We can see both transactions. So if we go back to this transaction, then we could see that in the logs we have the fulfillment of the request. So it's taking also a little bit. So let's go back to the okay, perfect. So here we see the randomness, and here we have the nonce, which is the nonce of the DRAND round. And basically, this is how we create the VRF task together with a Chainlink adapter. So far, if we have a look into our schema, we have learned how we create a simple contract inheriting some methods and the Gelato consumer base. We have created a task on Shape that listen to this event and execute the randomness. And later on, we have reused a contract that was created with Chainlink VRF in mind, so that the methods are the methods that the Chainlink adapter will expect. And we have created a task with Gelato VRF that at the same time deploys a Chainlink adapter that do the translation between the expected methods from the Chainlink adapter and the expected methods from the Gelato VRF. So the last question that, the last part that still we haven't looked at it is our is the part of the fallback. Sorry, VRF, the fallback part. So we call it here 0% missed events. So here we can call it fallback 1, and then we will set the address of the contract, which was this one, the simple VRF contract. We will say that we want every 30 seconds. And from block, we will then get the block of when we deploy the contract. So if we have a look here, that was created at this block. So we go to our creation of the task, and here we have that we want from this block that we create this fallback task that will check whether all of the events have been processed by our Web3 functions. So we're going to create the fallback. We're going to confirm. So let's wait until the fallback has been created. Perfect. VRF created successfully. And we have here the function that here we can see all VRF requests before block blah 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 were fulfilled. We're going to wait 30 seconds, and in the next 30 seconds is going to again check whether we have missed some events. These fallback functions are mainly used for production mainnet VRF task, because the protocols they want to ensure that none event has been missed. So here we see that 30 seconds afterwards, we do already the check, and we have here the answer: non-VRF requests were missed, all were fulfilled. So let me drink a little bit of water. So perfect. So to finalize, let's have a look at our docs, because we have already seen all of the different features that the Gelato VRF can offer you. How easy is to create the Web3 function, VRF task, how easy is to update your contracts or create contracts that are ready for consuming the Gelato VRF random words. So here if you go to docs.gelato.network, you have some videos for sure. We have the different parts of our docs: rollup as a service, rollups, Web3 service, and in the Web3 service part, we have VRF. Here is understanding VRF, where we explain how it works, more or less the same information that we discussed in the video. How does Gelato VRF works? At top level, we have a contract deployment, we request the randomness, we process the randomness event, and then we deliver. And here we have the different examples of the code that we have seen. So we have also the deploying your first VRF instance, how to do actually all of the steps that we just saw are here compiled. We also have migrating from Chainlink so that we can create chain compatible tasks where we deploy the adapter as we have seen before. Here is the pricing. There are two types of pricing. One is for every transaction that is executed on chain, there is a fee that will add on top of the cost of the transaction. And in the case that you have more than 200 requests per month, then you will have to pay some computational cost. But it's not often that VRF projects goes beyond 200 randomness requests. In case that you should go beyond this number, please contact us, and someone from the BD team will for sure walk you through. And here we have also all of the networks that we have where we are available. So I think this is all that I had to share with you. I don't know if there are questions on the chat. If you have questions about how the randomness work, or if I should dig in some of the pieces of the code, or whatever you would like that I go a little bit deeper, please drop the comment on the chat. I will wait 2 or 3 minutes. Well, there are no questions. So I think we can close here the streaming. Thank you very much for all of the watchers, and see you next time. Bye.